What if I told you, every wire, every circuit, every spark you see, follows a hidden set of powerful laws? From Ohm's law to Maxwell's equations. From tiny currents to massive power systems. This is not just electricity, this is the language of energy itself. In the next few minutes, you're going to see, not just learn, the most powerful electrical theorems and laws, in a way you'll never forget. Let's step into the world where physics becomes visual. Welcome to the universe of electrical tales. Hey friends! Today we're going to deeply understand one of the most important foundations in electrical engineering, Ohm's law. It's the key to knowing how voltage, current, and resistance work together. We'll break it down in the simplest way with real-life examples so that you'll never forget it. Let's dive in. Electricity is the flow of electrons through a conductor, just like water flows through a pipe. For this flow to happen, you need a push. This is called voltage. The amount of flow is called current, and the opposition to this flow is called resistance. Understanding the relationship between these three basic electrical quantities, voltage, current, and resistance, is essential in every electrical system. This relationship is defined by a fundamental rule known as Ohm's law. Let's travel back to 1827, to a small lab in Germany. Meet George Simon Ohm, a schoolteacher and scientist who loved tinkering with electricity. Scientists were experimenting with batteries and wires, but they couldn't predict how electricity flowed. Ohm noticed that some wires let more electricity through, while others slowed it down. He thought, there's gotta be a pattern here. So, he started testing different wires, batteries, and circuits, measuring how much current, the flow of electricity, came out when he applied a voltage, the push. Through careful experimentation, he observed that the current flowing through a conductor is directly proportional to the voltage applied across it, and inversely proportional to the resistance in the circuit. Thus Ohm's law was discovered in 1827. His work laid the foundation for the modern understanding of electricity, and his law is now a basic rule in electrical engineering, electronics, and physics classrooms around the world. The law is expressed in the simple formula V equals I times R, where V is voltage, in volts, I is current, in amperes, and R is resistance, in ohms. If you know any two values, you can calculate the third. This formula also gives rise to other versions. I equals V/R and R equals V/I. To make it easy to remember, people use the Ohm's triangle, where V is at the top, and I and R are at the bottom corners. Cover the value you want to find, and do the calculation with the other two. To make things clearer, imagine electricity as water flowing through a pipe. The voltage is like the water pressure, current is the flow of water, and resistance is like the width of the pipe. More pressure means more water flow, but a narrow pipe restricts the flow. Similarly, more voltage pushes more current, but more resistance limits it. This is a great way to visualize Ohm's law in a way that sticks in your mind. Let's take a few simple real-life examples. Suppose a 12-volt battery is connected to a 6-ohm resistor. Using Ohm's law, I equals V/R equals 12/6 equals 2A. That means 2 amperes of current will flow. In another case, if you want only 1 ampere of current to flow from a 10-volt supply, you'll need a 10-ohm resistor. These easy calculations show how engineers and electricians decide what components to use in a circuit. Ohm's law is everywhere around us, in phone chargers, LEDs, televisions, fans, and even in the circuits inside a remote control. For example, when you plug in your mobile charger, the internal circuit controls the current and voltage so your phone charges safely. Even small components like LEDs need correct resistors, or they might burn out. A simple 330 ohm resistor can protect an LED when connected to a 9-volt battery, proving how useful Ohm's law is in daily electronics. In electrical design, resistance is very important. If the resistance is too low, the current may become too high, overheating the circuit and causing damage. If the resistance is too high, devices may not work because not enough current flows. That's why designers calculate the correct resistance values using Ohm's law to ensure everything runs safely and efficiently. For those who want to feel the law practically, here's a simple experiment. Take a 9V battery, a few resistors, like 220 ohms, 470 ohms, and 1 k omega, and an LED. Try connecting different resistors and notice how the brightness of the LED changes. The higher the resistance, the dimmer the LED, because less current is flowing. This hands-on activity locks the concept of Ohm's law into your brain forever. Another important thing connected to Ohm's law is power. Power is the rate at which electrical energy is used. The formula is P equals V times I. Using Ohm's law, you can also write it as P equals I superscript 2 times R or P equals V superscript 2/R. These formulas help calculate how much power a device consumes, which is especially useful in designing electrical systems or choosing the right components for safe usage. To wrap it up, Ohm's law is one of the most important principles in electrical engineering. It was invented by George Simon Ohm in 1827 to explain the relationship between voltage, current, and resistance. It helps us calculate, design, and understand how electrical circuits work, from a simple flashlight to complex machines. The best way to learn it is to practice small examples and use visual tricks like the Ohm's triangle. Once you understand it, you'll never forget it, and you'll see how it applies to every circuit you build or use. Welcome to Electropolis, the most buzzing city of electricity. In this video, we'll explore Kirchhoff's laws not with formulas, but through an unforgettable story, fun characters, and simple logic. So grab your imagination and let's journey into the city where current flows like traffic. This is Electropolis, a city powered entirely by electrical rules. Let's meet the mayor, Kirchhoff. Every road is a wire, and electricity flows like traffic. This city runs perfectly, thanks to two ancient laws that keep everything in balance. Kirchhoff's current law and Kirchhoff's voltage law. Let's meet them. Rule 1, the roundabout law, KCL, Kirchhoff's current law. In the heart of Electropolis, there's a giant roundabout called junction. Every day, electric cars, current, enter this roundabout from different roads. Mayor Kirchhoff's made a law. The total number of cars entering junction must equal the total number of cars leaving. Why? Because there's no parking at the roundabout. Cars can't vanish or magically appear, they just flow through. So if 3 cars come in from the north, and 2 from the east, then exactly 5 cars must leave going south and west combined. This is Kirchhoff's current law, KCL. The total current entering a junction equals the total current leaving. In simple words, what goes in, must come out, at every junction. Sum of incoming equals sum of outgoing. Simple as balancing traffic. Rule 2, the loop law, KVL, Kirchhoff's voltage law. At the edge of town is a scenic circular train track called Voltage Valley. The train, a loop of electrons, goes around the whole track, passing through hills, batteries adding energy, and valleys, resistors using energy. Mayor Kirchhoff declared, when the train finishes one full round, the total energy gained must be equal to the total energy lost. So if the battery gave the train 7 energy points, and the resistors took 4 and 3 points, the train ends with 0, perfectly balanced. This is Kirchhoff's voltage law, KVL. The sum of all voltages in a closed loop is 0. The day the laws saved the city. One day, a sudden storm snapped a wire at junction 3. Cars, currents, got lost. Some roads overloaded. But the city's engineer, Mr. Ohm, used the two laws. He balanced the current at each junction with KCL and recalculated the voltage drops with KVL. Order was restored. The city ran smoothly again. Because an electropolis follows physics rules. Let's lock this in your memory with a quick recap. KCL equals, in equals out, like traffic at a roundabout. KVL equals, gains equals drops, like a train around a loop. Tips to remember forever. Roundabout. Think current law. Train loop. Think voltage law. Energy isn't lost, it just changes hands like currency in a perfect economy. Thanks for visiting Electropolis. Welcome back, travelers. Last time, we explored the lively city of Electropolis, where electrons zoom like traffic and rules of electricity govern everything. But today, we're diving deeper into the heart of the city. These aren't just rules, they are the core principles that every circuit obeys. In a vibrant electrical city Electropolis, two powerful laws govern everything. They are known as 1. King KCL, ruler of the nodes. 2. Queen KVL, ruler of the loops. In that first one is King KCL's rule, the gatekeeper of current. In Electropolis, at every intersection, node, King KCL has placed gatekeepers. Their job is simple. What enters a node must also leave. No soldier disappears or appears out of nowhere. Statement of this law. The algebraic sum of currents at any junction in an electrical circuit is zero. This law is based on the conservation of charge. Electric charge can't accumulate at a node. Therefore, the net charge flowing into and out of any junction must be zero. Here's some story to remember derivation of KCL. Electropolis Junction Jam. Welcome to the bustling current junction station in Electropolis. Here, Mr. Amp, the current traffic officer, ensures no charge ever gets lost at the intersections of the city. They arrive at a junction, the node. One day, Mr. Amp is posted at node J, a junction where wires from different directions meet. 3 electric vehicles, currents, arrive and depart. I1 and I2 are incoming currents, like buses arriving at the station with people, electrons. I3 is an outgoing current, a bus leaving with passengers. Count the currents. Mr. Amp has one rule. The number of passengers arriving must exactly equal those leaving, no one disappears or appears out of nowhere. So, if I1 equals 3A, I2 equals 2A, I3 equals 5A, then, KCL says, I1 plus I2 equals I3. Or rearranged, I1 plus I2 minus I3 equals 0. Let's go deeper. Why is this true? It is based on charge conservation. Electric current is the rate of flow of electric charge. At a node, no charge gets stored, no battery or capacitor at the node. So whatever charge enters must instantly leave. Therefore, sigma I in equals sigma I out. Sigma I equals 0. That's the derivation of KCL, it comes from law of conservation of electric charge. Mr. Amp logs the flow in his register. He smiles because no charge was lost, no electron went rogue, just like every day in Electropolis, where the laws of physics rule the streets. As the sun sets over Electropolis, King KCL nods with pride, every current accounted for, no charge lost, and perfect order at every junction. Somewhere beyond the nodes, in the silent loops and hidden paths of Electropolis, a new force awakens. Her name is Lady KVL, the guardian of energy and the ruler of voltage realms. Her story is not told at the junctions, but in the loops where energy flows and returns. What secrets lie within her circuits? What battles of voltage will unfold? The journey isn't over, it's only just beginning. Stay tuned for part 2, the loop of Lady KVL. A recap of King KCL's rule. In our last tale, we walked the busy streets of Electropolis, where King KCL ruled the junctions with a law as unbreakable as steel. He decreed, all the current that enters a node must leave it. Like guests entering and exiting a grand hall, no one gets lost. But balance at junctions was just one half of the story. Beyond those busy crossings, lay the winding circuits, the mysterious loops. But deep beneath the surface, far away from the light of the nodes, lies an abandoned mansion, known only as the Loop House. And it is ruled by none other than Lady KVL. Now entering the haunted Loop Mansion. On a stormy night, a young electrical apprentice named Elon receives a mysterious letter sealed with wax. The letter reads, "Come to Loop Mansion at midnight. Only then will you learn the true law of energy." Elon enters. The door shuts. Candles flicker. A shadow in a long gown appears. She's floating inches above the ground, cloaked in volts and mystery. It's Lady KVL. The curse of the closed loop. Lady KVL speaks slowly. "You seek the truth of the circuit, then walk the cursed loop with me." Elon walks a circular hallway, dimly lit, with 3 arched doors, R1, R2, and R3. Lady KVL whispers, "You start with power in your hand, from the voltage source, Vs. But beware. Each room you enter drains your energy." The 3 energy-draining rooms. Room R1. Walls lined with coils. It says, "I take IR 1 volts from you." Room R2. Floor covered in metal dust. Room 2 says, "Another IR 2 volts gone." Room R3. An electric mist. At final room 3, "Now surrender IR 3 volts." Elon feels weaker with each step. The law reveals itself. As Elon exits room R3, he returns to the entrance, empty-handed. The power he had at the start is gone. Lady KVL appears in full lightning form. Lady KVL told, "Vs minus IR1 minus IR2 minus IR3 equals 0. Or rearranged as Vs equals IR1 plus IR2 plus IR3. She holds up an ancient scroll that reads, "In every closed path, the total energy you start with must be completely spent. Nothing more. Nothing less." Elon said. "So, this is the Kirchhoff's voltage law." Lady KVL smiles. The ancient law, officially declared. Lady KVL declares, "In this mansion, and in every loop, whether real or imagined, what you gain is what you must lose. The sum of all voltages in a closed loop is 0. Sigma V equals 0. This law is based on the conservation of energy. Energy can neither be created nor destroyed, only converted from one form to another. If your sources give energy, your resistors must take it, always." As the apprentice leaves the mansion at dawn, he sees a statue of King KCL and Queen KVL in the garden. They rule not with swords, but with laws, unbreakable, unseen, yet eternal. King KCL rules the junctions. No current lost, no path ignored. Queen KVL guards the loops. What rises must fall, balance is law. Together, they protect the harmony of every circuit, from the tiniest bulb to the largest power grid. In your circuits and in your exams, never forget the two rulers of Electropolis. Kirchhoff's laws, simple, powerful, forever. Welcome to Hot Wire Cafe, the only kitchen in the city of Charlestown where electricity isn't just power, it's flavor. Today, we're stepping behind the scenes, into a sizzling story of how heat is born in wires. Meet Chef Toasty, the master of the kitchen, who reveals how tiny electric chefs cook up Joule's Law, the ultimate heat recipe. So grab your apron, sharpen your math spoons, and let's heat things up, one electron at a time. Let's travel back to the 1800s, to the town of Salford, England. There lived a curious young man named James Prescott Joule. While most boys played outside, Joule was busy heating water with electricity, just to see what happens. He wondered, if current flows through a wire, where does the energy go? Why do wires heat up? And after years of clever experiments, in 1841, Joule gave the world this powerful formula. H equals I squared times R times T. Heat produced equals current squared times resistance times time. That's why we call it Joule's Law. Imagine a glowing underground tunnel in the city of Julton, where tiny glowing workers called electrons run constantly, carrying energy from the power station to homes. This tunnel is a wire, and the roughness of its inner walls represents resistance. As more electrons rush through, they bump into the walls, and every bump releases a bit of heat. The more electrons, current, flowing, the rougher the tunnel, resistance, and the longer they run, time, the more heat gets generated. That's exactly what Joule's law explains. The heat produced in a conductor is directly proportional to the square of the current, the resistance, and the time of flow. The classroom in the kitchen, visualizing Joule's law derivation. Inside the cozy hot wire cafe, Chef Toasty gathers her team of trainee chefs, playful electrons, in a warm-lit classroom at the back of the kitchen. Standing by a glowing chalkboard, she begins, to understand how heat is born in wires, we must follow energy's journey. She sketches a battery, a wire, and a resistor, showing the chefs, current, running through the wire to power the stove coil. Power is energy flowing per second, she explains, writing P equals V times I on the board. Then, beside it, she draws a little clock. If our chefs cook for T seconds, the total heat is energy over time, H equals V times I times T. Sizzling coil animations appear behind her. Chef Toasty then recalls Ohm's law, V equals I times R, and substitutes it into the formula. The board glows with, H equals I squared times R times T. To make it memorable, she flips a chart showing, I equals chefs, R equals kitchen obstacles, T equals time on the stove, and says, more chefs, more struggle, more time, more heat. She draws a triangle with H at the top, I and R at the bottom. This is your heat triangle. The story flashes back to James Prescott Joule spinning paddles in water in his 1840s lab, discovering that mechanical work could be converted into heat. Energy never disappears, he says, it just changes form. As the camera zooms back to Chef Toasty, she ends, every time electrons hustle through resistance, they cook up the heat, and that's the true recipe behind Joule's law. And that's the story of Joule's law, where more current, more resistance, and more time means more heat. Just like a crowded kitchen with stubborn pots. The more hustle and effort, the hotter it gets. Chef Toasty's golden rule. H equals I square times R times T, where electrons turn work into warmth, and science becomes sizzling magic. From the kitchens of Joulestown to the wires in your home. Heat is not just energy, it's electrifying effort. Stay curious. Stay charged. And never forget, every law has a story, and every wire has a flame. The spark of Fluxington, Faraday's law of electromagnetic induction. Welcome to Fluxington, where electricity powers dreams. I'm Professor Maxwell, your guide to the city's greatest secret, Faraday's law of electromagnetic induction. This law lights our world, from transformers to your phone charger. Today, we'll uncover its history, meet the genius behind it, and derive it in a thrilling adventure. So, grab your attention, hit subscribe, and let's ignite the spark. The dark days of Fluxington. Long ago, in 1831, Fluxington was a sleepy village with no electric buzz. Power came from coal and steam, slow and smoky. Enter Michael Faraday, a British scientist born in 1791, a self-taught genius who loved experimenting with magnets and wires. Why did he invent this law? To unlock electricity's secrets. Faraday wondered, could moving magnets create electric current? His curiosity sparked a revolution. Birth of Faraday's law. He took an iron ring, like a closed racetrack. On one side, he wrapped a coil of copper wire and connected it to a battery. On the other side, he wrapped another coil, wired to a galvanometer, a needle that twitched if current flowed. He flipped the switch, nothing, but then, as he turned the battery off, it twitched, the needle jumped, then again, at every change. What? The current was flowing, but only when he started or stopped the battery. Not when it was steady. Faraday froze, a chill ran down his spine. It's not the magnet, it's the change in magnetism that brings electricity to life. Thus on August 29, 1831, Faraday's law was invented. The quest for the spark. Fluxington needs power, but the great transformer is failing. Guru Faraday tells me, use my law to create current with a magnet. Let's dive into Faraday's law and its derivation, like unlocking a treasure chest. Definition: Faraday's law of electromagnetic induction. Whenever the magnetic flux linking a coil changes, an electromotive force, EMF, is induced in it. In simple words, moving a magnet near a coil, or changing the magnetic field through it, creates electricity. Derivation as a story. Guided by a hologram of Michael Faraday, he embarks on a thrilling quest to unlock the secret of Faraday's law of electromagnetic induction, EMF equals -n d phi/dt. His journey unfolds in 5 magical steps, each a vivid mental image to sear the formula into your brain forever. First, he catches magnetic flux, phi, like raindrops in a net, phi equals b times a times cos pi. Next, he dances with a magnet, changing flux over time, d phi/dt, to spark electricity. Then, he stacks coils, n turns, like doses, multiplying the voltage. But nature fights back. A stubborn buffalo, Lenz law, adds a negative sign, resisting the change. Finally, the great transformer roars to life, lighting up Fluxington with the full formula, EMF equals -n time d phi/dt. The festival triumph. Thanks to Faraday's law, Fluxington shines. From 1831 to today, this law powers our world. Generators spin, transformers hum, all because Michael Faraday moved a magnet. In Fluxington, we honor him as the Spark King.
That's the spark of Faraday's law. Did you love this Fluxington adventure?
The coil that fought back, story of Lenz law. Long ago, in the magical land of Coileris, energy flowed not in silence, but in glowing copper rivers, and the guardian of balance was a quiet, powerful figure known as Master Lenz. In this world, a young inventor named Fluxen grew impatient with balance. He wanted speed, power, and transformation. One day, he climbed the tower of Coileris and dropped a legendary magnetic stone into the sacred coil to force energy into motion. But something strange happened. Instead of welcoming change, the coil fought back. A glowing blue current spun in the opposite direction, resisting the magnet's fall. From the mist appeared Master Lenz, holding the ancient mirror coil, and whispered, "Nature always resists the force that tries to change her." Confused, Fluxen demanded to know why the coil pushed against his efforts. Then, the ground lit up, and Lady Phi, the spirit of magnetic flux, emerged, dancing through the coil as the flux increased. As she moved faster, a golden ring of energy, EMF, electromotive force, formed around the coil, glowing brighter with every moment. Master Lenz traced the first law in the air. EMF equals d phi/dt. Explaining that the more rapidly the flux changes, the stronger this EMF becomes. But suddenly, a massive minus sign appeared and crashed into the formula, flipping it to EMF equals minus d phi/dt. As the induced current began to flow, not in aid of the change, but against it. This, said Lenz, is not resistance from hatred, it is resistance from duty. The induced current always rises in such a way that it opposes the very cause that created it, to preserve energy, to defend balance. As the magnet slowed in midair, held up by this opposing force, Fluxen finally understood, change without balance leads to destruction. This was not just a magical story, it was real. For in 1834, a real man named Heinrich Lenz observed the same law in his lab and gave it to the world. Definition of Lenz law. Lenz law states that the direction of the induced current in a conductor is always such that it opposes the change in magnetic field that caused it. Lenz law, expressed in one simple line. EMF equals minus d phi/dt. Tells us that whenever magnetic flux changes, nature always responds with a current that resists the change. That minus sign? It's the voice of nature saying, you may change, but not without consequence. And so, even today, whenever we move a magnet near a coil and feel that tiny pushback, we are feeling the hand of Lenz, still guarding the balance. Why was Lenz law needed? After Faraday's discovery of induction, 1831, scientists saw that a moving magnet could generate current, but they didn't understand the direction of that current. Sometimes it added power, other times it opposed motion. Why? Heinrich Lenz gave the missing piece. The direction of current is not random. It's governed by energy conservation. The induced current always resists the change that causes it. Without this, electrical machines wouldn't work predictably. Generators, motors, induction stoves, braking systems, none would be safe or efficient without Lenz law. Heinrich Lenz didn't discover opposition. He discovered balance. He showed us that energy cannot be stolen, only shared carefully. The next time you move a magnet through a coil and feel that little pushback. That's Lenz. Still watching. Still protecting the balance. The invisible push, story of Coulomb's law. Hi friends. Welcome back to Electrical Online, where we turn science into unforgettable stories. Today, we're diving into a law that explains why charges attract or repel, why electricity moves the way it does, and how the invisible push and pull of energy works. Get ready for the Coulomb's law, the law of invisible forces. But instead of boring equations, let's turn this into a magical story. The story of Chargeville, the land of charges. Long ago, in a floating world called Chargeville, lived two types of tiny glowing beings, positive charges and negative charges. The red-colored positives were always energetic, while the blue-colored negatives were calm and grounded. The most important rule in Chargeville was, opposites attract, and like charges repel. Whenever two positives or two negatives got close, they pushed each other away. But whenever a positive and a negative met, they were instantly pulled together. Like best friends reunited. The people of Chargeville lived by this strange invisible force but didn't understand why it worked, until a wise old scientist appeared. The scientist behind the law, Charles Augustin de Coulomb. In the real world, this law was discovered by Charles Augustin de Coulomb, a French physicist. In 1785, in France, Coulomb conducted brilliant experiments using a special tool called a torsion balance. He noticed that charged objects either attract or repel depending on their type, and the force they feel depends on how strong the charges are and how far apart they are. This became the world-famous Coulomb's law, which helps us calculate the electrostatic force between two charges. Definition of Coulomb's law. Coulomb's law states that the force of attraction or repulsion between two-point charges is directly proportional to the product of their magnitudes, and inversely proportional to the square of the distance between them. Mathematically, F equals K times Q2 divided by R square. This law explains the strength and direction of electric forces between any two charged particles. Derivation as a family story, understanding the formula. In Chargeville, the ruler was a mighty king named F, the king of force. But his strength didn't come from muscles, it came from his family. He had two powerful queens, Q1 and Q2, both were full of electric energy. The stronger these two queens were, the more powerful the king became. Their bond, shown as the multiplication Q1 times Q2, gave him energy. Beside them stood the loyal and unchanging royal guard, K, who made sure everything was fair and in balance. He represents Coulomb's constant. But their naughty son, R, always created problems. The farther the son went from the family, the weaker the king became, not slowly, but by the square of the distance R square. If the son doubled his distance, the king's power became 4 times weaker. That's why the strength of the king was always written as F equals K times Q1 times Q2, divided by R square. A perfect equation made of a family's bond, a soldier's discipline, and a child's distance. This simple story helps us remember that more charge means more force, and more distance means less force. Formula explained in simple words. The mathematical form of Coulomb's law is F equals K times Q1 times Q2, divided by R square. Here, F is the force between two charges, in newtons. Q1 and Q2 are the magnitudes of the charges, in coulombs. R is the distance between the charges, in meters. K is Coulomb's constant, 9 times 10 power 9 nm square divided by c square. So, the closer the charges, the stronger the force. The greater the charges, the stronger the force. And if the distance increases, the force drops rapidly. So now you know, Coulomb's law is not just a formula, it's a story of balance, distance, and electric love. From the smallest atom to the tallest lightning bolt, this invisible law is working every moment to create repulsion, attraction, and motion. And it all started with one curious scientist, one clever formula, and one kingdom of tiny charges. Hi friends. Welcome back to Electrical Online, where we turn tough concepts into simple, fun stories you'll never forget. Today's story answers a powerful question. How does electricity create magnetism? We've heard of magnets. We've seen wires carrying current. But what is the invisible connection between the two? Let's uncover the answer with the story of Ampere's law. Scientist history, the genius behind the law. In the year 1820, a scientist named Hans Ørsted noticed something strange. A compass needle moved when placed near a current-carrying wire. Electricity was creating magnetism. This news reached another brilliant mind in France, André-Marie Ampere. Inspired, Ampere wanted to find the exact relationship between electric current and the magnetic field it produces. After deep thought and experiments, he gave the world a rule, now called Ampere's law. It showed us. Current doesn't just move, it creates spinning magnetic fields around itself. This discovery became a foundation of electromagnetism, one of the four fundamental forces of nature. Story: The Circle Guardians of Current. Let's travel to a world called Electranagar, where all electric laws live as people. In this village, there lived a mighty king called Ishvar, the current king. Wherever Ishvar walked, strange things happened. Magical rings of spinning wind appeared around him. These were not ordinary winds. These were magnetoras, invisible magnetic fields that always moved in perfect circles around the current king. The stronger Ishvar's current, the stronger the magnetoras danced. But how do we measure these swirling forces? That's where a young curious boy enters. Derivation as a story. Imagine a small village where a current king named Ishvar lives inside a big circular fort. One curious boy named Balu, B, decides to walk around the fort on the wall. His tiny steps along the circle are called DL, daily little steps. As Balu walks, he feels a soft magical wind touching him. That's the magnetic field. He decides to note how strong the wind feels at each step, and by the time he finishes the full circle, he adds up all the wind he felt. This total is written as conterintegral B times dl. Suddenly, the wise village elder Acharya, Mu, appears and says, that wind isn't just nature, it's caused by the current king Ishvar sitting inside the circle. The more powerful Ishvar's current is, the stronger your swirling wind will be. Then he smiles and gives the golden rule. Conterintegral B times dl equals mu times I. Which means, total magnetic wind along Balu's circular path equals Acharya magic, mu, times, current king Ishvar's power, I. Now Balu knows, walk in a full circle, measure the magnetic wind, and you'll know how strong the hidden current inside really is. That's Ampere's law, magnetic wind always circles current. Formula explained simply. The real scientific version of the law is conterintegral B times dl equals mu times I, enclosed. This says, the total magnetic field, B, around a closed loop, dl, is directly proportional to the current, I, passing through that loop, multiplied by the constant of magnetism, mu. Where conterintegral equals integration along a closed loop. B equals magnetic field. dl equals small element of the loop. Mu equals permeability of free space. I equals enclosed current. Definition of Ampere's law. It states that the line integral of the magnetic field, B, around a closed path is equal to the permeability of free space, mu, multiplied by the total current, I, enclosed by that path. Mathematically, conterintegral B times dl equals mu times I. In simple words, whenever electric current flows through a wire, it creates invisible circles of magnetic energy around it, like spinning wind. If you walk in a full loop around the wire and measure the magnetic force at every step, then add it all together, the total magnetic force you feel is always equal to the current flowing inside the loop, multiplied by the magical strength of space, mu. That's Ampere's law. It tells us how magnetic fields swirl around current like loyal bodyguards. So friends, whenever you switch on a fan, or hear a transformer buzz, just imagine. Ishvar the current king is walking again. Balu is taking his loop path. And the magnetoras are spinning silently, forming invisible circles that keep our world moving. This is the magic of Ampere's law, and now, it's not just a formula, it's a story in your mind. Once upon a time, in the year 1800, in a quiet village called Biot-Savart, a strange rumor began spreading. Villagers who sat near a glowing copper wire during festivals claimed they felt a strange breeze in the air, but only near the wire, and only when it carried current from the temple bell to the village lights. What was causing this invisible swirl? Was it a ghost? Was it wind trapped in metal? No one knew. Until one day, a young boy named Viru, the son of a lamp maker, began to chase this mystery. Scientists' history, Biot-Savart's curious journey. Far away from the village, in France, lived two brilliant minds, Jean-Baptiste Biot and Félix Savart. In 1820, after hearing about Hans Christian Ørsted's discovery that electric current affects a magnetic compass needle, they grew obsessed. What if every wire carries with it an invisible storm? Biot asked. So, the two began to investigate, not just if magnetism happens, but how much, where, and why it happens. And thus, after deep experiments and mathematics, they created a law that described exactly how magnetic fields form around moving charges. That law became known as the Biot-Savart Law. Biot-Savart Law, magical ripple story. One day in village of Biot-Savart, Viru watched his grandfather stir tea with a spoon. As the spoon moved, little ripples formed in the tea. Suddenly, Viru imagined, what if this spoon was a wire carrying electric current? And these ripples were magnetic fields? His grandfather smiled and said, that's exactly what the Biot-Savart Law tells us. If you take a tiny piece of wire carrying current, it sends out invisible ripples, magnetic fields, in all directions. The closer you are to the wire, the stronger the ripple. And the direction depends on how the wire is placed. Viru's imagination made it clear, a tiny current element acts like a magical ripple maker, spreading magnetic energy around it, just like the spoon in a cup. In simple words, Biot-Savart Law states that a small piece of a current-carrying conductor produces a magnetic field around it, and the strength of that field at a point depends on the current, the length and direction of the wire, the distance from the point, and the angle between them. Derivation: the brotherhood of the magnetic field. Once upon a time, in the heart of Biot-Savart, a glowing baby named mu0/4 pi, mu/4 pi, was born under the northern lights, a symbol of universal balance. Though small, he was powerful and wise. As he grew, he gathered 4 magical friends to help him understand and shape the world of invisible forces. Current, I, a bold warrior, always in motion. He carried electric energy through wires and was the heartbeat of every circuit. DL, a tiny but clever wire sprite who lived along the electric path. He guided current through every twist and turn, lighting up villages as he passed. Arhat, a swift and sharp-eyed hawk who always flew from the sprite toward the sky, pointing the direction where the magical force would act. R², a mysterious cloud spirit who believed that the farther the distance, the weaker the influence. No one can escape me, he often whispered. Now, these 5 set off on a journey. Whenever current passed through wire ELF, DL, they sent a signal to direction hawk, R, who flapped his wings and marked the location. But their power didn't just shoot straight, it twisted. Thanks to the magic of the cross product, cross, the resulting magnetic force always curled around like a ring, like the swirl of wind around a tree. Together, they wrote this magic rule. dB equals mu/4 pi, multiply, I times dl times sin theta, /r². Each term a living force, each interaction a memory. When they combined their powers across the entire wire, they generated the total magnetic field, an unseen force felt by compasses, metals, and minds. Simple memory trick. Imagine a boy standing next to a river of current. He throws a stick, dl, into the wind, our direction. The stick swirls in a circular path, that swirl is the magnetic field. The farther you go, r², the weaker the swirl gets. And the whole process is scaled by a magical constant, mu/4 pi. Why it's used? To calculate the magnetic field at any point in space caused by a current-carrying conductor, especially when the wire is bent or shaped in a complicated way, like loops or curves. Where it's used. To find magnetic field in coils and loops, in electromagnets and transformers, in designing MRI machines, electric motors, generators, in physics simulations and magnet design. And that's the story of Biot-Savart Law. When current flows, it creates tiny magnetic circles around it. Just like how every small action can create a big effect. So next time you switch on a light or charge your phone, remember, a silent magnetic dance is happening behind the scenes. Electricity isn't just power. It's a story, a swirl, a law of nature. Keep learning, keep exploring. The sparks that changed the world. In a time before LEDs, before smartphones, even before electric fans, there was a world powered only by steam, oil lamps, and dreams. A world that was just beginning to understand the invisible force called electricity. But this new force had no map, no guide, no way to measure how much power it really had. People saw lights glow and motors spin, but no one could explain how much energy was being used or needed. That's when one man's quiet brilliance lit the path ahead. His name was James Watt, and the law he discovered would become one of the most powerful tools in all of electrical engineering. This is not just a formula, it's a story. The story of Watt's law. History, the man behind the measure. Let's travel back to 1781, in the misty hills of Scotland. Inside a small, smoky workshop filled with steam engines and copper wires, a man sat at his wooden desk. James Watt had already revolutionized the steam engine, but his curiosity had grown deeper. He was no longer just interested in motion, he wanted to know how much power it took to create that motion. How could we measure the strength of electricity? How do we know if a machine is powerful or weak? James Watt believed that this hidden force could be calculated, and so, he worked night after night. One evening, as rain poured outside his window, Watt connected the dots between pressure, flow, and the work done. From that moment, Watt's law was born, and it gave the world the ability to measure electrical power with accuracy. The unit of power was named after him, the Watt. Story, the secret equation of Watt-Nagar. In a faraway city called Watt-Nagar, energy flowed through the streets like water in pipes. Wires ran underground, glowing slightly with a blue pulse. Machines worked, but nobody really knew how much energy they were using. Some machines heated up, others flickered, and chaos grew. The people were scared, until three mysterious beings arrived. The first was Power, a brave hero with unstoppable energy. He had the ability to make things move, spin, and shine. But power was lost without help. The second was Voltage, a powerful but unpredictable force. He pushed energy with great pressure, but too much push could break things. The third was Current, a calm and loyal messenger. He carried the energy through wires like a river flowing through a city. Together, they formed the legendary team, P equals V multiply I. It means that power is born when voltage gives a push, and current carries that push forward. If either V or I is missing, power cannot exist. The people of Watt-Nagar cheered. Now they could control their machines, balance their energy, and live without fear. From then on, every engineer, electrician, and scientist remembered their names. This wasn't just a discovery, it was a law. Definition: Watt's law in simple words. Watt's law explains how much electrical power is used in a circuit. It tells us that the power, how much work is being done or energy used, is the result of two things. How strong the push is, called voltage. How much flow is happening, called current. So, power is simply the product of voltage and current. The stronger the push and the more the flow, the more power is consumed. It's like water in a pipe. The higher the pressure and the faster the flow, the more powerful the water blast will be. From the rainy streets of 1780 Scotland to the glowing circuits in your home today, Watt's law lives on. It powers your fan, your fridge, your phone, and your future. So the next time you switch something on, remember, P equals V times I. Power is never magic. It's a perfect team of pressure and flow. If this story helped you understand what's law in a way you'll never forget. The magical story of capacitance. Long ago, in 1745, in a Dutch town called Leiden, a professor named Peter van Musschenbroek was experimenting with electricity. One stormy night, he filled a glass jar with water, placed a metal rod inside, and touched it. Suddenly, a powerful spark leapt out and shocked him. Surprised and amazed, he cried, "This jar can store electricity." This became the world's first capacitor, the Leyden jar. From that moment, scientists realized that electricity is not only something that flows but also something that can be stored and released like treasure in a box. Now, let's enter the Temple of Plates, where two shiny golden plates stand tall. These are not ordinary plates but penny plate 1, P1, and penny plate 2, P2. Living in this temple are two playful twins, Quin positive, Q plus, and Quin negative, Q minus, bundles of electric charge. They love sitting on the plates, but they need help to move. Their helper is Vinny voltage, V, who gives them the push they need. Separating the plates is a caretaker, David dielectric, D, who ensures they don't touch but still keep their attraction strong. When Q plus and Q minus settle on the plates, something magical forms, Captain Capacitance, C, the guardian of stored energy. In this magical temple, a law is revealed, and the definition of capacitance is written in golden letters. Capacitance is the ability of a system to store electric charge per unit voltage across it. Mathematically, this is expressed as C equals Q slash V, where C is the capacitance, Q is the charge stored, and V is the voltage applied. Now let's uncover the deeper magic of this temple. The shiny plates have an area A, which decides how many quins can sit comfortably. The caretaker, David dielectric, separates the plates by a distance D, making sure they don't touch. But he also adds his secret power, a special property called permittivity, epsilon, which tells how easily the electric field can form between the plates. Together, these factors shape the strength of Captain Capacitance. The law of the temple reveals the full formula, C equals epsilon times A slash D. This means the capacitance increases if the plates are bigger, if the plates are closer together, or if the space between them is filled with a stronger dielectric material. And so, from a simple Leyden jar in 1745 to the magical capacitors inside our phones, computers, and cameras today, capacitance has shaped the world of electricity. Remember, capacitance is the ability to store energy and release it when needed, like a treasure chest of sparks. The story of Gauss and his two laws. Far away, in a land called Feodoria, people often wondered about the invisible forces that ruled their world. They saw sparks of electricity, they felt the pull of magnets, but no one could explain why these mysterious fields behaved the way they did. One day, a wise traveler named Carl Friedrich Gauss arrived in Feodoria. The villagers gathered around him, curious to hear what secrets he carried. With a gentle smile, Gauss said, "I will tell you two truths of nature. Listen carefully, for if you see the story in your mind, you will never forget my laws." The first truth, electricity and the palace of charges. Gauss led them to a grand crystal palace, inside which sat King Q, glowing brightly. From him, tiny shining messengers flew outward in every direction. These messengers were none other than electric field lines. A child asked, "If we build a wall around this palace, how many messengers will pass through the wall?" Gauss raised his staff and said, "No matter what shape your wall is, round, square, or jagged, the total number of messengers depends only on how powerful the king is, his charge Q." He explained, "This is Gauss' law for electricity. The total electric flux through any closed surface equals the enclosed charge divided by epsilon 0. Phi E equals, contra integral E times, dA equals, Q slash epsilon 0. To make them understand, Gauss called upon two helpers. Eddy the electric field, E. Aerial the area patch, dA. Eddy pushed through Ariel's little patch, creating one tiny messenger, E times, dA. When every patch on the wall joined, the villagers saw all the messengers together, the great sum. Contour integral E times, dA. And Gauss declared, this equals Q/epsilon 0, the power of King Q himself. The villagers nodded in awe, now seeing electric charges as kings whose messengers pass through any wall surrounding them. The second truth, magnetism and the endless river. Then Gauss took them to the Valley of Magnets. Here, shimmering rivers of magnetic field lines flowed endlessly in loops, weaving across the sky and back into the ground. A villager asked, where is the magnetic king? Where is the single pole that sends out these rivers? Gauss shook his head. Children, no such king exists. Unlike electricity, magnetism has no single charges. Every north pole is forever tied to a south pole. The rivers never begin and never end, they only flow in closed loops. He revealed the second truth. Gauss' law for magnetism, the net magnetic flux through any closed surface is always zero. Phi b equals, contour integral b times dA equals, 0. Once again, Gauss called helpers. Benny the magnetic field, B. Ariel the area patch, dA. Benny flowed into Ariel's surface patch, but just as much left through the other side. When the villagers added up every patch, the total was 0. Gauss smiled. This means magnetic field lines never start or end. They always come in pairs, always loop forever. The villagers now pictured magnets as eternal rivers, flowing endlessly without a beginning or end. The legacy. As the villagers of Fieldoria cheered, Gauss reminded them. Electricity, a king, charge, sends messengers, field lines. Flux equals Q/epsilon 0. Magnetism, no king exists. Rivers of field lines loop forever, so flux is always 0. Years later, the great scientist James Clerk Maxwell would gather Gauss' two truths along with Faraday's and Ampere's into his legendary scrolls, the Maxwell's Equations. These four equations became the heart of electromagnetism, guiding the world into a new age of science. Outro, eternal memory. And so, in Fieldoria, even children remembered the tale. A glowing king with messengers passing through every wall means, Gauss' law for electricity. A river of magnetism that never begins and never ends means, Gauss' law for magnetism. Gauss' two truths live not as formulas on paper, but as unforgettable stories etched in their imagination forever. The Magical Kingdom of Inductance, a Grand Cinematic Tale. In the year 1831, the world stood at the edge of a new electrical age. In England, Michael Faraday made a spark of discovery. While across the ocean in Albany, New York, Joseph Henry unlocked the same secret almost at the same time. Their experiments showed that when current flows through a coil, it creates a magnetic field, and when that current changes, it pushes back with a voltage of its own. This magical property was called inductance, and the world honored Joseph Henry. The word inductance itself was later introduced by the scientist Oliver Heaviside in 1886, and the unit Henry, H, was named in honor of Joseph Henry. The magic spells of inductance. In the shining kingdom of Indaria, this discovery came alive as a grand tale. At the heart of the land ruled the wise King El, whose crown was made of endless coils. His people asked, "O mighty king, what is your secret power?" And he lifted his staff to reveal. L equals N phi/I. The power of inductance, he said, is the ratio of turns and flux to the current that flows. But danger lurked in shadows. The rebel sorcerer Epsilon hated sudden change. Whenever current tried to rise or fall, he roared like thunder, self-induced EMF. Epsilon equals -L di/dt. His curse shook the skies, he always opposed change. Yet, not all was dark. The twin princes, Qualuz and Fluxor, shared a magical bond. Whatever one brother did, the other instantly felt. Their connection was called mutual inductance, written in the Golden Scrolls as M equals N2 times Phi21/I1 equals N1 times Phi12/I2. Beneath the palace, a glowing vault was guarded by Lady W, the keeper of energy. Her lantern shone whenever current flowed, whispering, energy in inductor. W equals half Li square. The more the current, the brighter I store energy, she declared. And in the farthest corner of Indaria, the ancient tower architect built the mighty solenoid tower, etched with its eternal truth, solenoid formula. L equals mu n square A/L. The more the turns, the bigger the area, the stronger the core, the greater the inductance. But the longer the path, the weaker it becomes, he proclaimed. As the story ended, the skies of Indaria glowed with the symbols of L, epsilon, M, W, and the tower. From that day, the world remembered, inductance is the silent force that resists change, stores energy, and binds coils together. So, whenever you see a coil, remember this story, because inside it lives a kingdom of magic and science. Imagine a world where invisible forces govern magic-like phenomena all around us, light blinking on and off, electricity powering our cities, magnets pulling and pushing. For centuries, people wondered, are electricity and magnetism related? How does light travel through space? The answers to these mysteries wouldn't arrive until one extraordinary man wove them together through the power of math. The man behind the magic, James Clerk Maxwell. Born in 1831 in Edinburgh, Scotland, James Clerk Maxwell was a curious boy with a love for mathematics and science. By the time he was 14, he published his first scientific paper, a hint of the genius to come. Maxwell studied at Cambridge University, emerging as a brilliant mathematician and physicist. In the mid-1800s, scientists had discovered many surprising facts. Electric charges create forces, Coulomb's law, magnets have north and south poles, and changing magnetic fields can induce electricity, Faraday's law. But these findings felt like pieces of a puzzle, disconnected and mysterious. The quest, Maxwell's brilliant insight. Maxwell's goal was to bring all these discoveries into a single, elegant framework, to reveal the hidden connections between electricity, magnetism, and even light itself. From 1856 to 1865, Maxwell worked tirelessly. He translated Faraday's experimental observations into mathematical formulas, invented new concepts like the displacement current, and finally wrote down 4 equations that described all known electromagnetic phenomena. In 1865, Maxwell stunned the world by showing that light is an electromagnetic wave traveling through space at a fixed speed, the speed of light. One stormy night, Maxwell dreamed he entered a giant ancient hall. In the center was a glowing scroll floating in the air, but it was locked by 4 symbols. A voice whispered, "To see the truth, you must face the 4 guardians." The first door opened, and from the light emerged the guardian of electricity. He held a shining sphere of charges, and said, "I am the law of electric fields. All charges create electric fields, and the total field around me is equal to the charge inside." Suddenly, the scroll lit up with the first symbol. Nabla times E equals, ρ/epsilon naught. The ground shook, and a second door opened. Out came the guardian of magnetism, carrying a steel ring that looped forever with no start and no end. His voice was heavy like thunder. "Unlike charges, magnetic poles cannot exist alone. My field lines always loop, they never break." And the scroll revealed the second carving. Nabla times B equals 0. But the hall grew darker, and a crack of lightning split the sky. The third guardian appeared, cloaked in blue flames, the keeper of changing fields. He raised his staff and said, "When magnetic fields change with time, they give birth to electric fields that swirl endlessly." The scroll burned with the third truth. Nabla times E equals, minus, del B/del T. Maxwell trembled as the last guardian rose, taller than all the rest, with coils of light wrapped around him. He was the guardian of Ampere and Maxwell, the unifier. His voice echoed like 1,000 drums. Electric currents, and even changing electric fields, create magnetic fields that circle around them. The final symbol appeared, glowing brighter than the sun. Nabla times B equals mu naught J plus, mu epsilon naught, del E slash del T. The hall blazed with light as the scroll unlocked. Maxwell opened it and gasped. The four guardians together revealed that electricity and magnetism were one, and even light itself was an electromagnetic wave. The hidden scroll of the universe had been read at last. Maxwell's equations told a story of unity. Electricity, magnetism, and light are all part of the same electromagnetic symphony vibrating through the universe. Thanks to Maxwell's vision, modern technologies were born, from radios and TVs to lasers and Wi-Fi. His equations predicted radio waves even before their discovery, linking physics and everyday life. Maxwell passed away in 1879, but his legacy lives on in every flicker of light and every signal sent across the globe. In the mystical land of Electrica, for hidden powers whisper in the shadows. King Charge releasing invisible arrows. Lady Surface weaving her glowing net. Sir Area stretching the boundaries. And Wizard Divergence guarding the final truth. Their secret binds the universe, but only through Gauss Law can we unlock it. Hi family, welcome back. In the previous video, we explored the very basics intro of Maxwell's equations, and today we dive deeper into the first one, Gauss Law for electricity. If you're like this channel, hit like and subscribe. Let's aim for 1K likes. Now, let's step into the story and uncover how this magical law reveals the hidden source of electricity. Imagine a magical lake called Electrica, filled with invisible electric fish swimming through the waters. These fish are the electric field lines emitted by electric charges, carrying their power everywhere. At the heart of this lake is King Charge, who releases countless electric fish. These fish radiate outward, growing fewer as they swim farther. Following a law, the electric field strength decreases inversely with the square of the distance. E equals Q slash 4 pi epsilon naught r square. Lady Surface surrounds King Charge with her magical net, made of many tiny windows, each counting the electric fish swimming through. The total fish count is called electric flux. Phi E equals contour integral S E times dA. Sir Area tells Lady Surface, the total surface area of her net is 4 pi r square, because the fish swim straight outward and cross the net perpendicularly. The total fish crossing equals fish density times net area. Phi E equals E times 4 pi r square. Lady Surface substitutes King Charge's fish density, E, into the flux expression. Phi E equals Q slash 4 pi epsilon naught r square times 4 pi r square equals Q slash epsilon naught. This means no matter how big the net, the total fish passing through depends only on the number of fish inside, the charge enclosed. The lake fills with many charges, each releasing their own fish, creating a complex swarm. General ρ is the charge density, the number of fish sources per unit volume inside Lady Surface's net. The total charge enclosed is Q enc equals integral V ρ dV. Lady Surface's flux count generalizes to Phi E equals 1 slash epsilon naught integral V ρ dV. Wizard Divergence introduces a powerful tool, the Divergence Theorem, which says that the total fish Lady Surface catches on her net equals the sum of local fish spreading out from every point inside the net. Contour integral S, E times dA, equals integral V, nabla times E, dV. Because this principle applies everywhere, the local spread of fish equals charge density divided by permittivity. Nabla times E equals ρ slash epsilon naught. By counting these invisible fish crossing Lady Surface's net and understanding how they spread inside the net, we fully grasp the magic of Gauss' law, a law that reveals how electric charges govern forces unseen but deeply felt. Gauss' law says, the total electric flux, total fish passing through Lady Surface's magical net, equals the total electric charge inside, number of fish sources, King Charge plus others, divided by a special number called permittivity of free space. Written as Phi E equals Conterintegral S, E times dA, equals, Q anc/ epsilon naught. This means, no matter how big or oddly shaped the net is, the total fish counted only depends on how many fish sources, charges, are inside the net. Next, we'll dive into the next great discovery in electromagnetism, another of Maxwell's powerful equations that unveils how changing electric fields create magnetic waves. You pick up a burger and try to eat only the top bun. But magically, the bottom bun always sticks with it, no matter what. Now, what if I told you magnets are exactly like this? Magnetic poles are never alone and always come in pairs. If that made you curious, hit like, subscribe, and let's dive into this magnetic mystery. Imagine you're at a magical burger shop and you ask for only the top bun of a burger. The chef smiles and says, "Sorry, you can't get just one bun. Our burgers always come with both the top and bottom buns stuck together like best friends who never want to be apart." This is exactly how magnets work. You can never find just a North Pole or just a South Pole by itself. No matter how many times you cut a magnet, it will always have both poles together, like inseparable burger buns. This is what Gauss' law for magnetism says. The total magnetic field lines passing through any closed surface is zero. In other words, magnetic field lines always make loops. They don't start or end, they never appear alone, just like the two buns of your burger always come together. Step-by-step burger derivation. Step 1. Count the burger layers, magnetic flux. Imagine magnetic field lines as layers of a burger sliding through the burger box's lid. The flux is how many layers cross the surface. Phi b equals, integral S, B times dA. B equals magnetic field, the delicious burger layers. dA equals tiny patch on the burger box's surface. Step 2. Wrap the burger box, closed surface. Wrap your burger tightly in a box. Now ask, how many burger layers pass through this box? Every layer that slides in on one side must slide out the other side. So the total number of layers coming in equals the layers going out, making the net zero. Conterintegral S, B times dA, equals 0. Step 3. Chef's quality control, divergence theorem. The chef checks every inch inside the burger, volume, to make sure no layers mysteriously appear or disappear. Conterintegral S B times dA equals integral V nabla times B dV. Because the flux through the burger box is always zero, this means nabla times B equals 0. No burger layer, magnetic field line, has a start or end point, they're endless circles of yum. Thanks for sticking with me through this magnetic burger adventure.
Ladies and gentlemen, welcome to the Science Premier League, where today's match isn't about runs or wickets, it's about currents and fields. Introducing the teams. Team Magnetic Field, B, calm, invisible, and very attractive. Team Electric Field, E, fast, energetic, and led by none other than Virat-Kohli. The umpire Faraday announces,
whenever the magnetic field inside the ground changes, Virat-Kohli, the electric field E, must start running around the boundary. That's the main rule of the game, and it's actually Faraday's law.
Hey friends. Before we start this story, just tap that like button, hit subscribe, and share it with your friends, so we can spread a little more electric fun together. Alright, let's jump into the story.
Think of the ground as a big surface, A, and inside it, magnetic field lines go up and down. The total number of magnetic lines passing through it equals magnetic flux, phi b. It can be written as phi b equals integral B, d times A. So, magnetic field lines through the ground equals magnetic flux. When those magnetic lines increase or decrease, the crowd, electric field, gets excited and starts running around the boundary line, path. That running energy around the boundary is called EMF, epsilon, the electric thrill, created by the magnetic change. That EMF we written as epsilon equals minus d phi b slash dt. So when B changes inside, E runs around outside, that's the main idea. Now, the total run Coulomb makes around the stadium equals the line integral of E around the boundary. Epsilon equals counter-integral E times dl. So both ways describe the same EMF, one by field change inside, one by field movement outside. By equating the both sides we get counter-integral E times dl equals minus d slash dt integral B times dA. Now, imagine a drone camera flying above the stadium. It sees Coulomb's circular running pattern from above. That pattern is called the curl of E. By using Stokes' theorem we written equation as counter-integral E times dl equals integral nabla times E times dA. Combine it with the earlier equation. Integral nabla times E times dA equals minus d slash dt integral B times dA. Let's assume the ground isn't moving, only the magnetic field lines are changing. That means we can move the time derivative inside. D slash dt integral B times dA equals integral del B slash del T times dA. Now, integral nabla times E times dA equals minus integral del B slash del T times dA. Faraday declares,
This rule holds true for every patch of the ground, no matter where Coulomb runs. So if it's true for every surface, then even the integrands must be equal point by point. Nabla times E equals minus del B slash del T.
Faraday holds the mic and explain.
When the magnetic field inside changes, the electric field runs around outside. And it always runs opposite to that change. That's why the negative sign appears. It's Coulomb saying, I'll oppose whatever change happens in the magnetic field.
Just remember this small story in your brain. A cricket ground, surface, full of magnetic lines. Coulomb runs around it whenever those lines change, and his running pattern is opposite to the change. From that one image, the entire derivation flows automatically in memory. Phi b equals integral B times dA equals lines through the ground. Epsilon equals minus d phi b slash dt equals change makes EMF. Epsilon equals counter-integral E times dl equals Coulomb runs. Combine equals counter-integral E times dl equals minus d slash dt integral B times dA. Use strokes equals nabla times E equals minus del B slash del T. That's Maxwell's third equation, remembered forever as when magnetism changes inside, electricity runs around outside. And that's how the electric field was born. But wait, the story continues. In the next video, Maxwell's fourth equation enters the ground. With Ampere and Maxwell in one shocking combo. Don't miss it, like, subscribe, and stay charged.
Welcome back, future engineers. Today we unlock one of the most powerful equations in physics. Maxwell's fourth equation, also called the Maxwell-Ampere law. Before we start, hit that like and subscribe button. Not because I asked, but because Maxwell deserves it.
Once upon a time in the world of science, electricity and magnetism lived like two powerful brothers, always arguing about who was greater. Electricity bragged, I power cities, technology, lightning, I am the king, while magnetism folded his arms and said, without me, motors stop, compasses fail, and even you can't move properly. Scientists watched them like strict teachers watching naughty students. Then in 1820, in France, a calm genius named André-Marie Ampère entered the scene. He observed quietly, discovered that when electric current flows through a wire, magnetic field circles around it, and proudly wrote the law. Counter-integral B times dl equals mu naught I. Everyone celebrated, electricity smiled wide, see? When I move, magnetism follows me like my bodyguard. Magnetism stayed silent, but deep inside, he knew the story wasn't finished. Time passed, and in 1861 at Cambridge University, England, a quiet, sharp-minded scientist named James Clerk Maxwell picked up Ampere's law and whispered, beautiful. but incomplete. He pointed at a charging capacitor. Electrons never cross the gap, yet magnetic field still exists there. If no current flows, how does magnetism appear? Nature never breaks its rules, continuity must always exist. So Maxwell introduced a brilliant idea, displacement current, where changing electric field acts like current inside the capacitor gap. ID equals epsilon naught d phi e/dt. With one stroke, he upgraded Ampere's law into a perfect, complete truth. Conterintegral b times dl equals mu I plus epsilon d phi e/dt. Electricity's jaw dropped, magnetism smiled proudly, and Maxwell placed his pen like a king laying down a sword after restoring balance. Suddenly, a miracle happened. Electricity said, if I change, I create magnetic field, and magnetism replied, and if I change, I create electric field. They realized they were never enemies, they were partners. This is Ampere, Maxwell law definition. The magnetic field around a closed loop is produced not only by electric current, but also by a changing electric field. In formula form, conterintegral b times dl equals mu naught I plus epsilon d phi e/dt. In this, conterintegral b times dl equals total magnetic field around loop. Mu naught equals magnetic strength of space. I plus epsilon d phi e/dt equals total current, real current plus displacement current. In that moment of unity, light was born, not from wires or flames, but from electric and magnetic fields dancing together forever. That gentle correction written in 19th century England did not just solve an equation, it created sunlight, stars, radio, Wi-Fi, X-rays, satellites, modern civilization itself. And the universe whispered, nature never breaks continuity. Changing electric field creates magnetism. Changing magnetism creates electric field. They chase each other across space, making electromagnetic waves, the light that fills our world.
And that, my friends, is Maxwell's fourth equation, the law that united electricity and magnetism and lit up the universe. If this story made science feel simple and beautiful, subscribe, like and share with one friend so more minds can glow like light itself. Imagine a tiny tea stall where the chai is boiling and suddenly 3 customers slam their orders at the same time. One wants extra strong, one wants low sugar, one wants his first. The tea nearly spills, the seller freezes, then calmly says, if all of you shout together, everything will burn. I'll handle you one by one. And that single chai rule is the entire idea behind the superposition theorem.
Right after this moment, we connect to the real history. The idea of superposition comes from Hermann von Helmholtz, a German scientist in 1853, who discovered that in any linear system, you can simply add individual effects to get the total effect. Engineers later applied this directly to circuits. Let one source act at a time, turn the others off, find each effect separately, and then add them up. Now let's jump into our story. In a small town called Circuity, there was a tiny tea shop run by a hard-working man called Uncle Resistor R. Every morning he served tea peacefully, until one day 3 customers entered the shop at the same time. The first one was voltage guy V1, loud and energetic, shouting, "Uncle, serve me first. I'm the important one." The second customer, voltage lady V2, shouted even louder, "No, serve me first. My voltage is higher." The third was current boy I1, who didn't shout but kept moving around, pushing everyone like flowing current. All 3 talked, pushed, and complained at the same time. The tea shop became chaotic, just like a circuit with multiple sources attacking a poor resistor. Uncle Resistor R cried, I cannot understand who wants what. One at a time, please." Suddenly, the wise village leader Sir Superpos entered the shop, rang a bell, and declared, "From now onwards, only one customer will speak at a time. Others must remain silent." This was the superposition rule. Superposition theorem definition. In any linear circuit with more than one independent source, The total current or voltage is equal to the sum of the currents or voltages produced by each source acting alone, with all other sources turned off. This can be expressed as V total equals V1 plus V2 plus V3 plus so on, plus Vn, or I total equals I1 plus I2 plus I3 plus so on, plus In, where Vn and In are the individual voltages and currents from each source. Then the calculation began. First, only voltage V1 was allowed to speak. Voltage V2 went silent, short circuit, and current I1 went outside, open circuit. Uncle R worked and calculated the current he produced with V1 alone. This current was called I1. Next, only voltage V2 was allowed to speak. V1 went silent, I1 again went outside, and Uncle R calculated another current, called I2. Finally, only current boy I1 was allowed to speak. Both V1 and V2 slept on the floor, short circuits, and Uncle R calculated the third current called I3. Sir Superpos then happily announced, total current through Uncle R equals I1 plus I2 plus I3. And that, he said, is the meaning of superposition theorem. Let's see an example. Suppose in a circuit, V1 produces 2A through a resistor, V2 produces 1A, and the current source produces 3A. If we follow our T-shop method, one at a time, we simply add them. Total current equals 2 plus 1 plus 3 is equal to 6A. Just like 3 customers ordering separately and Uncle R's total work being the sum of all 3. Now here's how you will remember superposition forever. Think of voltage sources as loud customers who lie on the floor when off. Think of current sources as calm customers who step outside when off. Think of resistors as Uncle T Master R. And imagine Sir Superpos entering your mind saying, one at a time. Every time you see a circuit with multiple sources, this T-shop scene will replay in your mind automatically.
And that brings us to the end of this story. Superposition theorem is nothing but a simple life rule. When too many sources shout at once, make them speak one by one, calculate their effects, and add everything. Just like a calm chai seller handling one customer at a time, we handle one source at a time in a circuit. If today's story made this concept stick in your mind forever, then mission complete. Thank you for watching, keep learning, stay curious, and I'll see you in the next electrifying video.
Hi friends, welcome to my channel ElectricalTales. Let me ask you one simple question. Have you ever opened a circuit diagram, seen resistors and wires everywhere, and thought, where do I even start? Today's circuit looks exactly like that. But the goal is very small. Find the current through just one resistor. Here's the secret. You don't need to solve the whole circuit. We can shrink the entire network into one battery and one resistor. This small idea is called Thevenin's Theorem. Today I'll explain it like a simple story, step by step, so even beginners can understand. If you are new here, please subscribe and let's aim for 50 likes. Now come, let's enter an electrical workshop and meet today's hero, Mr. Thevenin. Imagine a small electrical workshop in the evening. Only one bulb lights the room. On the table lie wires, resistors, batteries, and meters. On the blackboard, there is a big and confusing circuit. Wires cross everywhere. It looks scary. A student looks at the board and says nervously, "Sir, this circuit is too big. How do we even start?" The teacher smiles and says, "Don't worry, let me tell you a story." The teacher points to the circuit and begins. More than 100 years ago, in 1883, in France, an engineer named Léon Charles Thevenin had the same problem. He worked with telegraph circuit. Those circuits were very long and very complicated. Every time a new device was connected, engineers had to solve the entire circuit again. Thevenin got tired and thought, why should I solve everything again and again? Then he had a simple idea. When a load is connected to a circuit, the load only sees two terminals. It doesn't know what is happening inside the circuit. So, from those two terminals, even a very big circuits behave like a small simple circuit. The teacher arranges the board, then he draws one battery and one resistor in series. The students look surprised. Here, we start with the definition. The teacher says slowly, this is called Thevenin's Theorem. Thevenin's Theorem says any large and complicated electrical circuit can be replaced by one voltage source VTH, one resistance RTH in series when seen from the load terminals. This small circuit gives the same voltage and current to the load as the original big circuit. Now the teacher writes on the board the formula. Thevenin's voltage VTH is equal to open circuit voltage across the load terminals. Thevenin's resistance is the RTH, resistance seen from terminals after the turning of all sources. And next, load current IL is equal to VTH by RTH plus RL. He says these three formulas are enough to solve many exam problems. Next part is derivation. Now the teacher says let's do the simple workshop job. We can take some simple steps. In that first one, remove the load. First remove the load resistor. Forgot it for a moment. Next step, we have to find Thevenin's voltage. Now measure the voltage across the open terminals. This open circuit voltage is called VTH. Next find the Thevenin's resistance. Now turn off all sources. Voltage source, short circuit, current source is open circuit. From the same terminals, calculate the resistance. This is RTH. Next we need to build a small circuit. Now draw one battery of value VTH and one resistor of the value RTH in series. Reconnect the load. And the last, the teacher connects the load again. The bulb glows exactly the same as before. The teacher smiles and says, see, the circuit looks different, but it behaves exactly the same.
Let us solve the given circuit using Thevenin's theorem. Our aim is to find the current through the load resistor 6 ohms. First, remove the 6 ohms resistor. Now to find Thevenin's voltage. After removing the load, only 2 ohm and 4 ohm resistors are active. They are in series. So the total resistance is 6 ohms. Supply voltage is 6 volts. So the current is 1 ampere. Voltage across the 4 ohm resistor is V equal to I times R. So 4 into 1, 4 volts. So the final VTH Thevenin's voltage is equal to 4 volts. Now a common doubt. Why don't we consider the right side 2 ohm resistor? Because the load is removed, that side is open. Open circuit means no current. No current means no voltage drop. Next, to find the Thevenin's resistance. Turn off all voltage source. Replace it with a wire. Now we have 2 ohm in series and 2 ohm in parallel 4 ohm. Parallel value is 1.33 ohms. So the final RTH is equal to 2 ohm plus 1.33 ohms. By the final value, RTH is equal to 3.33 ohms. Now reconnect the load resistor. The load resistor is 6 ohms. So the total resistance is R total equal to RTH plus RL, which means 3.33 ohms plus 6 ohms. The final answer is 9.33 ohms. To find the load current, IL is equal to VTH by R total equal to 4 by 9.33. In the final, the load current is 0.43 ampere. We didn't solve the full circuit. We changed the big circuit into a simple voltage and resistance. This is how Thevenin's theorem makes circuit problems easy and simple. We didn't solve the full circuit. We changed the circuit into simple battery and resistance. That is why Thevenin's theorem makes circuit problems easy and fast. If this story helped you understand Thevenin's theorem, please give this video a like. And if you are preparing for exams or want concepts explained in simple, story-based way, don't forget to subscribe the channel. Hi friends, imagine you are a tiny little resistor and you are stuck between two angry uncles fighting every day. One uncle is super strong, 28 volts. The other uncle is sneaky, 7 volts. And both of them are shouting, current will go through my side. No, through my side. Meanwhile you, the poor resistor, are like, bro, I am just 2 ohms. Please tell me how much current is actually going through me. Sounds confusing, right? But what if I told you there's a 100-year-old magic trick that turns this giant messy circuit into something super small and super easy? That magic trick is called Norton Theorem. So come, let's jump into the story. Once upon a time, there was a glowing electrical town called Norton Nagar. In the middle of the town lived a small register boy named Ravi. Ravi was only 2 ohms, but every day he was stressed because on the left side Ravi stood a powerful uncle with 28 volt station with 4 ohm gate. On the right side stood another uncle with 7 volt station with 1 ohm gate. Both uncles kept pushing electricity toward Ravi, and Ravi kept thinking, why is my life so complicated? How much current is really flowing through me? One quiet night, under the shining stars, a glow appeared in the Norton Nagar. A kind old man with white hair, a warm smile, and a small toolbox walked into the town. Ravi looked up and asked, Uncle, who are you? The old man smiled and said, My name is Edward Norton. Then he said something interesting. A long time ago, around 1926, I worked in a famous lab in America called Bell Laboratories. At that time, engineers were solving big messy circuits every day, and it was taking too much time. He continued, We already had a brilliant trick by Thevenin. He showed how to shrink a big circuit into one voltage source and one series resistor. By the way friends, if you haven't watched my Thevenin Theorem video, please watch it after this one. It will make today's concept 100 times easier. And if you are new to this channel, welcome to ElectricalTales. Here, even difficult circuits become simple stories. So, subscribe and stay with us. Norton smiled and said, but many engineers prefer thinking in terms of current, not voltage. So, I create current version of this theorem. And that theorem is called Norton's Theorem. Ravi eyes widened. So, uncle, what exactly is the Norton magic? Ravi, my theorem is very simple. Any big, complicated circuit, when seen from 2 terminals, can be replaced by just 2 things. One current source, called Norton current, IN. One resistor in parallel, called Norton resistance, RN. And the best part, this small Norton circuit give me the same effect as the big original circuit. Ravi jumped happily. So, my entire town can become small? Yes, Ravi. Now watch the magic. In first step, remove the load. Norton gently told Ravi, Ravi, step aside from the movement. Ravi moved away. And now the 2 terminals were empty. In next step, find Norton current. Norton placed a thin shining wire between those terminals. This wire has 0 resistance. The current flowing through it is called short circuit current. And that short circuit current is called Norton's current, IN. Now Norton calculated. From the left uncle, 28 divided by 4 equal to 7 ampere. From the right uncle, 7 divided by 1, 7 amperes. Both currents met at the short wire. So, total IN equal to 7 plus 7, 14 ampere. Ravi was shocked. 14 amperes? That's huge. Yes, Norton Nagar can push 14 amperes if it is shorted. In third step, find Norton resistance. Now, Norton removed the wire and said, next we find Norton resistance RN. For that, we turn off all independent voltage sources. And he explained simply. When a voltage source is turned off, it becomes a wire. Now only the resistors remain, 4 ohm and 1 ohm. They are in parallel. So Rn equal to 4 parallel 1. That means 4 times 1 by 4 plus 1 equal to 0.8 ohms. Norton said, so Norton resistance is 0.8 ohm. And the last we have to find Norton equivalent circuit. Suddenly, the entire Norton Nagar shrunk into a tiny circuit. A 14 ampere current source in parallel with 0.8 ohm resistor. That's it. This tiny circuit is the Norton equivalent of the whole town. Now, Norton placed the Ravi back in his position. The circuit became peaceful. Ravi stands in parallel with Norton's 0.8 ohm resistor, and the Norton gently explains that they must find the total resistance. Together they calculate 1 by RT equal to 1 by 0.8 plus 1 by 2 equal to 1.25 plus 0.5 equal to 1.75. So the final resistance equal to 0.571 ohms. Then using Ohm's law, V equal to 14 amperes times 0.571 ohms equal to 8 volts. Ravi happily realizes that the voltage across him is 8 volts. So Ravi's current is I equal to 8 divided by 2, 4 amperes. Ravi clapped happily. Finally, I got it. So the current through me is 4 amperes. Norton laughed. Yes, Ravi, you don't need to fear of big circuits anymore. As the sun rose over Norton Nagar, Edward Norton packed his toolbox and started walking away. Before leaving, he turned back and said, whenever a circuit looks big and scary, don't fight it, just shrink it. Ravi waved goodbye and shouted to everyone in the town. Friends, big circuits are not difficult. They just need Norton magic. So friends, next time you see a huge circuit in your exam or project, don't panic. Just remember Ravi and Norton Nagar. First step, remove the load. Second step, short the terminals and get I and Norton current. Third step, turn off sources and get Norton resistance. And final step, you have to draw the Norton equivalent and solve easily. And just like that, confusion disappears like a magic. Hello everyone. Today we are going to understand a very simple and important concept in electrical engineering. By the end of this video, we will know why a bulb sometimes becomes dim even when the battery is fully charged. If you find this explanation helpful, please like this video. Let's aim for 20 likes. And don't forget to subscribe for more simple electrical concepts. Now, let's start the concept. Imagine this situation. You connect a fully charged battery to a bulb. The bulb glows bright. Everything looks perfect. You feel happy and step away for 5 minutes. But when you come back, the bulb is dim, almost off. There is no broken wire, no short circuit, no power cut. The battery is still connected and it even feels a little warm. So, what happened here? Did the energy disappear? No, energy never disappears. It only changes form. Here's the important point. A battery is not perfect. Inside every battery, there is something called internal resistance. Think of it like a small resistance hidden inside the battery itself. When current flows through the circuit, not all the energy reaches the bulb. Some of the energy is lost as heat inside the battery. That is why the battery feels warm. So the dim bulb is not because of power vanished, but because some power was wasted as heat. Now comes the main concept. Long ago in 1840, an engineer named Moritz von Jacobi noticed the same problem while working with electrical motors. He discovered something very important. If we want maximum power to reach the load, whether it's a bulb or a motor or a speaker, the load resistance must be equal to the internal resistance of the source. If the load resistance is smaller, too much current flows and more energy becomes heat. If the load resistance is larger, less current flows and the output becomes weak. But when both resistance are equal, the power delivered to the load becomes maximum. This idea is called the maximum power transfer theorem. Load resistance equals source internal resistance. Mathematically, R1 equals RTH and the maximum power transfer formula is V squared divided by 4R. Now remember something interesting. At this condition, efficiency is only 50%. That means half the power is still lost as heat. But this is the point where the load gets the highest possible power from the source. So what really happened in the garage? Battery was strong, the bulb was fine, but there was not matched. And when the load resistance doesn't match with the source internal resistance, maximum power cannot be delivered. Some energy becomes heat, some is wasted, and the output becomes weak. But when both resistance are equal, system works it best. This is the idea behind the maximum power transfer theorem. This principle is not just a classroom theory. It is used in speaker and amplifier matching, antenna and radio systems, solar MPPT controllers, and even fast charging technologies. Engineers constantly try to match source and load to extract maximum usable power. So, next time you see a dim bulb, don't immediately blame the battery. Check the balance, because in electricity and even in life, the right match makes the all difference. Follow for more simple electrical stories explained in an easy and interesting way.
Hi friends, welcome back to Electrical Tales, where circuits are not boring, they are stories never forget. Today, I am going to tell you a story, and by the end of the story, compensation theorem will be locked in your brain forever. Close your eyes for a second and imagine a peaceful village called Circuit Villa, where electricity flows like a beautiful river. Lights glowing, fans spinning, everything is perfect. This flowing river is our current I. And far away there is a powerful dam pushing the water, that's our voltage, V0. But this river is not free. It has to pass through some obstacles. Near the dam there are fixed rocks. We call them as RTH. And at the village gate there is a big stone, that's RL, the load. So because of this, the flow becomes I equal to V0 by RTH plus RL. Very simple. More resistance means slow current, less resistance means fast current. Everything is going smoothly until one day a naughty kid named Delta comes quietly and drops a tiny stone at the village gate. Now resistance becomes RL plus delta R. And suddenly the entire current slows down. Lights become dim, fans slow, villagers are panicked. They ask, do we have to solve the entire circuit again? That sounds painful. Long calculations. Then a wise engineer walks in with a smile. He says, no need to solve everything again. We will use a shortcut, compensation theorem. Listen carefully. This is the whole idea. Whenever resistance changes, imagine a backward pump. Instead of changing the resistor, we imagine placing a small backward pump at the location. This pump pushes against the current. Compensation theorem definition. When a resistance in a circuit is changed by a small amount, delta R, the effect of this change of current can be found by adding a voltage source equal to I times delta R in the same place, acting in the opposite direction, while replacing original sources with their internal resistance. This means if a resistor changes, we don't solve the whole circuit again. We just imagine a small backward voltage source, I times delta R, at the place to find how current changes. And its strength is very easy. Vc equal to I times delta R. Whole current multiplied by change in resistance. That's it. Now the uncle quickly show a simple 3-step derivation. First, the original current, I equal to V0 divided by RTH plus RL. After adding the extra stone, I dash equal to V0 divided by RTH plus RL plus delta R. Now the changing current, delta I equal to I slash minus I. When we simplify this, we get delta I equal to minus I times delta R divided by RTH plus RL plus delta R. The villagers look confused for a second, but the uncle smiles and says, look at that minus sign. It means the change is in the opposite direction, backward. So instead of writing the full expression, we simply say delta I equal to minus Vc divided by total resistance. And suddenly everything makes sense. The slowdown caused by the extra stone is exactly the same as the effect of that tiny backward pump. No need to redraw the circuit. No need for long calculations. From that day, Circuit Villa never panicked again. Whenever resistance changed, they just imagined the backward pump and solved everything in seconds. What if I tell you something surprising? In one special circuit, you can swap two positions and nothing changes. The circuit stays the same, the resistors are same, and even after swapping, the current is still the same. Sounds strange, right? But this is the real rule in electrical engineering called Reciprocity Theorem. In the 1800s, electricity was still a mystery. Scientists were trying to understand how current flows in a circuit. Two famous scientists, Hermann von Helmholtz and Gustav Kirchhoff, were studying simple electrical networks.
During the experiments, they placed a voltage source in one branch of a circuit and measured the current in another branch. After solving the circuit, they got a certain current value. Then they tried something different. They swapped the positions of the voltage source and measuring branch. When they solved the circuit again, they noticed something amazing. The current value stays exactly the same. This interesting discovery became known as a Reciprocity Theorem. Simple definition. Reciprocity Theorem says that in a linear circuit with only one source, if we swap the position of a voltage source and the branch where we measure the current value remains the same. In very simple words, swap the source, current is the same. One simple electrical story. Imagine a small place called Electric City. In this city, there are 3 roads called R1, R2 and R3. On the left side lives Mr. Voltage. His job is to push electrical charges into the city. On the right side lives Mr. Current. His job is to count how many charges arrive. One day, Mr. Voltage pushes the charges into the road. The charges travel through R1, pass through R2 and R3. Mr. Current counts them and says 10 charges arrived. Everyone remembers the number. Next day, they decide to try something fun. Mr. Voltage and Mr. Current swap houses. Now, Mr. Voltage stands on the right side and Mr. Current stands on the left side. But the roads of the cities remains exactly the same. Again, charges travel through the same path. When Mr. Current counts them, the result is still 10. Nothing changed. Everyone in the city laughs and realizes that swapping their position didn't change the result. This is exactly what Reciprocity Theorem means. How to verify this theorem? First, to check the Reciprocity Theorem in a circuit, first choose 2 branches. One branch where source is connected and another branch where the current is measured. Then solve the circuit and find the current value. After that, swap the positions of the source and the measuring branch. Solve the circuit again and find the new current. If both currents are equal, then reciprocity is proven. This rule is worked when the circuit is linear, there is only one independent source and there is no one direction devices like diode. If these conditions are not satisfied, the result may be changed. Easy way to remember. Whenever you hear Reciprocity Theorem, just imagine Mr. Voltage and Mr. Current swapping their houses in electrical city. Even after changing places, the number of charges arriving remain the same. This simple imagination will help you to remember the concept forever. 3 voltage sources are connected to one point, each trying to control the voltage. But shockingly, the final voltage doesn't belong to any one of them. Sounds impossible, right? But this is one of the most interesting secrets in electrical engineering. Welcome to Electrical Tales, where we turn complex concepts into simple stories you'll never forget. Let's imagine a simple situation. There's a big water tank and 3 people are filling it with water. Person A with high pressure, person B with medium pressure, person C with low pressure. But here's the twist. Person A uses a thin pipe, person B uses medium pipe, person C uses wide pipe. Now think, who will control the final water level? The one with highest pressure or the one with biggest pipe? Take a guess. Actually, none of them fully controls it. The final water level becomes a balanced mix of all 3. This is exactly what happens in the circuits. Water pressure means voltage, pipe size means resistance, tank means node. When multiple sources are connected to one node, the final voltage is shared. Definition. Millman's theorem says, when several voltage sources with resistance are connected to a common node, the voltage at the node is the weighted average of all source voltages. Formula is V equal to V1 by R1 plus V2 by R2 plus V3 by R3 divided by 1 by R1 plus 1 by R2 plus 1 by R3. Don't worry about the formula. Just think like this.
Each source contributes based on its voltage, its resistance. Lower voltage means more flow, it means more control. Higher resistance means less flow, means less control. Just think as an example. It's just like a group decision. Not the loudest person wins, not the weakest person loses. The final result depends on everyone's influence. So, now you know how the final voltage is decided. But here's a challenge for you. If one resistance becomes very small, will that source dominate completely? Comment your answer below and I will explain in the next video. If you love learning electrical concepts through stories, don't forget to like, share and subscribe to Electrical Tales. Because here every concept has a story. Thank you.